So let's proceed. What is a property package? A property package is a collection of calculation methods specific to a chemical engineering application. So there are some differences in the definition of a property package depending on the simulator you're using. For example, in HYSYS, the property package doesn't include the compounds, but it already includes the equilibrium calculation methods and the phase property calculation methods. A property package in HYSYS is composed of these two modules. Okay. In Coco Simulator, the things are a little bit different because according to the KP Open definition, the property package should include the compounds and the equilibrium calculation methods and the phase property calculation methods. Everything must be in a closed package. In DWSIM, I choose to follow more or less like HYSYS does. I let the user choose the compounds independently of the property package, which only includes the phase property calculation methods, and the component responsible to calculate the equilibrium phase distribution is the flash algorithm, as I'll show you later. So that depending on the property package, such as the steam tables and the aqueous electrolyte property package, the soil water property package, they all have their own equilibrium calculation methods because it is very specific for the application of these methods. Okay, so but the vast majority of the property packages in the DWSIM, they depend on the flash algorithm to calculate the phase distribution. So this is why I put yes and no in this box here. So as I just told you, the DWSIM property package, they include the calculation methods only, and the compounds can be selected independently. And the equilibrium calculation is done by another component, which is the flash algorithm. These are the property packages that you can find in DWSIM. For an ideal gas or ideal solution, you can use the Rhodes Law property package. For non-ideal liquid mixtures, you can use an activity coefficient model like UNIQUAC and NRTL, modified UNIFAC, the Dortmund version, modified UNIFAC, the NIST version, or UNIFAC. Okay, for a high precision property, a simulation where you need high precision properties, you can use CoolProp. For instance, if you have a refrigeration simulation, you can use the CoolProp because it contains specific compounds for this kind of application. And for water and steam simulation, you can use the steam tables, and if you have water with salt, you can use the seawater property package. For hydrocarbons, I suggest you to always use the Penn-Robson equation of state because it works very well for hydrocarbons at low and high pressures, and if it doesn't work, in some cases you can switch to the SRK iOS. The Lee-Kessler blocker model is there for in case these two equations of state fail. You can also use the Penn-Robson Strict-Vera 2, but the DWSIM doesn't have any interaction parameter for this equation of state. And you can also switch to the Penn-Robson with Lee-Kessler enthalpy and entropy method if for some reason you're not liking the values generated by the Penn-Robson equation of state. Okay. For hydrocarbons with hydrogen, you can use the Charles-Cedar model or the Grayson-Street model. They are very specific for this kind of simulation. And for special cases like the aqueous electrolytes, you can use the extended Uniquac, although it doesn't have all the parameters required for all ions, so you must use it with caution. For gas and oil industry, when you don't have information about your oil, you can use the black oil model. And for soil water, including hydrogen sulfide and CO2 and etc., you can use the soil water model. I'll talk a little about these models in a moment. You can also download the external property package libraries like the Advanced EOS library, the ThermoC library. They both are available in the DWSIM website for you to download for free. And DWSIM also features a KP Open socket where you can include an external property package from another simulator, another library, and use it in the DWSIM. Okay. So the KP Open socket is already included with the DWSIM, and for these other two libraries you can go to the DWSIM website and download them. Let me show you how. You will find the specific pages for these components in this side menu here. So this is the one for the ThermoC library, and this is the one for the Advanced EOS library. For the ThermoC, you can see information about it. And down there on the page, you will see the download links here. Download the package and follow the instructions, and you are set. The same is also true for the Advanced EOS library. You can see the download links here depending on your operating system. Download and follow the instructions for installation and usage, and you're set. For the KP Open socket, I'll get into details in another course, but this is how it works. You can create a new simulation, and the compounds should come with the property package. So assuming that you're trying to simulate a water system and you want to use the Cocoa water property package, you select the KP Open and click on Add, and you will be presented with this screen where you will select the KP Open version. 1.1 is the most recent one. Then select the property package manager. It should be T. And here you will see a list of the predefined property packages. This one is for water and butanol using the Uniquac model. Okay, and if you click on Edit, it will show the configuration window for this property package coming directly from the Cocoa thermodynamics server. Okay, so you can see that you have two components. You can click OK, go back to the compound selection, add in butanol, one butanol, which is the same, and there on the configuration window for the KP Open, you should go to the compound and component mapping tab, and you will see that it is already correctly mapped, because you must do the mapping from the compounds in the DWSIM to the compounds in the KP Open property package, because they will be calculated inside all properties will be calculated inside the property package and will be mapped to the compounds in the DWSIM manually in the code. Also the phase mapping, you can see that the property package from the Coco simulator only supports one vapor and one liquid phase. You can see that the DWSIM can support 3 liquid phases, including a aqueous one and also a solid phase, but since they are not supported by the KPOpen property package, you must leave them disabled. Okay, so with this you've already had set up your KPOpen property package. You could continue your simulation normally without any problems. Okay, but this was just to show you how the KPOpen socket works. So regarding the property package in the DWSIM, we have an object-oriented model where there is a base property package which has a common set of methods. These methods calculate the molecular weight of the mixture and the thermal conductivity and the viscosity of the phases. Okay, then each property package has its own models to calculate the fugacity, the entropy, the heat capacities, the compressibility factor, the density, isothermal compressibility, the Book modulus, the speed of sound, Joule-Thomson coefficient. Okay, so each property package has a different method to calculate these properties, but for these three here, the DWSIM uses the same methods to calculate them. So this is like it is property package independent set of models. And for single compound properties, in these latest versions of the DWSIM, if the database contains experimental data, we will always use it. Otherwise, we will use some correlations to estimate the properties. Let me show you an example in the code. Okay. If we open the DWSIM thermodynamics project, which is where all models are coded, you can see that we have a base class for the property package, which is the skeleton for the property package. It also includes most of the methods to calculate the KPOpen implementations, interface implementations. Let me show you, for instance, how we calculate the liquid thermal conductivity. So this is the routine that calculates this property for an individual compound, and you can see that if the compound has an equation defined in the database, or it is not an ion, or it is not a salt, the DWSIM will use the information from the database to calculate the property. So the returned value will come directly from the database, using the database coefficients. Otherwise, if we don't have any experimental data available, we use a correlation based on Latini's method to calculate the liquid thermal conductivity. So this will be used only if we don't have experimental data available. Okay, guys. We will see this with more detail with the solution inspector at the end of this course. Okay. So about the DWSIM flash algorithms, they calculate the distribution of the compounds in the supported phases at the defined conditions like temperature, pressure, entropy, and vapor fraction. of the overall mixture. Okay, and the supported specs in pairs are the temperature and pressure, temperature and vapor fraction, pressure and enthalpy, pressure and entropy, it should be an S here, and pressure and vapor fraction. These two are the bubble and dew point routines mainly. The TP1 is the most basic flash algorithm. It is used by most unit operations and is the basic method to calculate the equilibrium in the material stream. As you can see, I'll show you later. And the supported equilibrium phrases, they depend on the flash algorithm, but in the DWSIM you will have flash algorithms which support a vapor and one liquid phase, one vapor and two liquid phase, two liquid phase only, one solid and one liquid, and vapor, solid and liquid phase all in the same mixture. Again, we have some special cases, which is the steam tables, which deals with water only, and we don't have a flash algorithm to that elaborated to calculate. Just some simple math is enough to calculate the equilibrium conditions for water. And the black oil property package also has its own flash algorithm, the aqueous electrolytes methods too, and the saltwater model, which also includes a chemical equilibrium calculation for the species in the mixture. It also needs a more elaborated flash algorithm, which is not available for selection if you're using another property package. Okay, so the flash algorithm selection in the DWSIM, this is my recommendation. If you have if you expect only to have one vapor and one liquid phase, you should stick with the nested loops VLA flash algorithm, and if it doesn't work, you should switch to the Gibbs VLA. If you expect to have two liquid phases, you can use the nested loops VLA, and if it doesn't work, you can switch to the Gibbs one with support for two liquid phases. If you have only two liquid phases, you can use the simple LLA, otherwise you can switch to the nested loops VLA flash algorithm. And if you have a solid phase, you can use the nested loops SVLA flash algorithm. There is a special case. If you have hydrocarbons with water, you can use the nested loops immiscible VLA flash algorithm, which is very fast for this kind of calculations. Otherwise, if you need to calculate the solubility of water in the hydrocarbons or vice versa, you can use the nested loops VLA. And if it doesn't work, so you can use the inside out VLA flash algorithm. So let's try some of them in the DWSIM now. Here it is. And we have a condition at which we will have a liquid vapor equilibrium. You can see that the calculated vapor molar fraction at 200 Kelvin is 0.24, and if you click on phase properties, the DWSIM will calculate all properties of all phases. Okay, so this result is a consequence of the property package and the flash algorithm that you've selected. So for instance, if we change the property package from SRK to ideal, for instance, Rhodes law, and let's the DWSIM calculate the equilibrium again pay attention to the vapor phase amount, you can see that it is a lot different, and you should be able to know why this happened. I won't tell you. I will create a quiz for you to answer this question for me, okay? This is the list of the flash algorithms that you have added to the simulation. You can choose from this list, and you can see that you can select the Gibbs, for instance. You don't need to remove it. You can keep more than one, but I'll show you the result of the calculation. It shouldn't change that much because these flash algorithms support the same set of phases, and they calculate the equilibrium through different methods, but they should always give you the same result. Okay, so if you notice, due to numerical approximations, you can see that the number is almost the same, except for the 1, 2, 3, 4, 5, 6th decimal case. See? Let's try Lee-Kessler blocker model. We got something closer to the SRK result. You'll notice that each time we change the property package, or we add a different package or flash algorithm, it also updates the editor for the selected object in the flowsheet, and you can scroll down to the property package settings and select from this list. See, the default flash algorithm is always the first one in the list, okay? So, which is why there is this item default by default, because the DWSIM will try to use the first one always when you don't manually select a flash algorithm from this list. You can also access the configuration windows for the property package and the flash algorithm from these little buttons here. Okay, but this is for you to see how they work. Let's try a solid liquid equilibrium problem here. Let's try with water and ethanol and NRTL as the proper package, and the SVLA nested loops flash algorithm, which supports the solid phase. So let's drag a material stream to our flow sheet. You can see that we already, at the standard conditions, we already have the equilibrium calculated. No vapor, no solid, only liquid. Okay, so let's cool down this mixture a little bit to 260 Kelvin. Let's see if we get a solid phase. Not yet. Oh, here we have it. So the nested loops SVLA flash algorithm calculated at these conditions a solid phase containing only water. The liquid phase lost a little water in the process, obviously. And if you click on phase properties, you will see the amount of the solid which appeared in the mixture here. Okay? If you change the flash algorithm to a VLA option, like the nested loops VLA, which is the default one, you will see that the solid phase will vanish, because this flash algorithm is not capable of calculating a solid phase in equilibrium with liquid and vapor. Okay, so I hope this helped you to understand how the flash algorithms work in the DWSIM. We will get into more detail later about it, but this is it. Okay. So now let me show you how to manage the property package and the flash algorithms in the cross-platform interface. Let's open it. Let's create a new simulation. I'll close the wizard just to show you where you can set up your property package. You can go to Setup, Flowsheet Settings, or click here in the Settings button. They all open the same window. Sorry, in the Basis window. Here you can see that you can add a new property package by selecting an item from this list. So let's add the NRTL, and the flash algorithm you can add one from this list here. Okay, that's it. And let's set up the compounds just to make an example calculation. Now I'm going to do something different with you. This mixture is known to form an unstable liquid phase at some specific mixture composition at the ambient conditions. So let me show you how this works. If you use an equimolar composition with the nested loops VLA flash algorithm, the DWSIM will calculate at these conditions we will have one liquid phase only, and the DWSIM will calculate its properties, everything is okay. But I know that if we have 0.9 water and 0.11 butanol composition, we will have two liquid phases, but the selected flash algorithm isn't capable of calculating that. So we need to change the flash algorithm to one of the VLLA methods. So let's choose the Gibbs minimization VLLA. Let me remove that one, and I'll edit it just to show it, to make sure that it will calculate the equilibrium, but I will show you how this works later. Okay, so let me click to solve this. Thing again, and you will see that the Gibbs VLLA flash algorithm calculated two liquid phases and some residual vapor phase, which is a characteristic thing of this minimization method. But I'll show you later that this is the real result. In real life, at these conditions, we would have two separated liquid phases in the mixture. And you will see that you need to select a flash algorithm which is capable of predicting the liquid phase instability and the liquid phase splitting. Okay, guys, so you can see that we have a second liquid phase, and the DWSIM calculates its composition, which is made mainly by water, a little alcohol, but here is it. So as you may have noticed it already, in the DWSIM you can mix multiple property package and flash algorithms, and the selection is made at flowsheet object level. Okay, so let me explain this to you using the classic interface. Now I will reopen our example from task 2 from the previous course. Here we have our material stream, and if you go to the edit simulation settings window, basis, you will see that we can add more than one property package, okay, more than one flash algorithm. You can add more than one copy of the same flash algorithm because they can have different settings. You can have different options for the flash algorithms of the same type. The same is also true for the property package itself. You can add more than one copy of the same flash algorithm. For instance, if you pretend to use different interaction parameters for these property packages, and at flowsheet level, at object level, you can select the property package to use and the flash algorithm that you wish to use for that single object, not only for material streams but for unit operations as well. They all have this property package settings selection, except for a few ones, and I'll show you why. For instance, if you add a heat exchanger, you have this selection, but the DWSIM will actually use the selections from the material streams connected to the heat exchanger. You will ignore this setting to keep the energy balance closed in the heat exchanger, so we must obey the selection made at the material stream level for the material streams connected to the heat exchanger. Okay, so this is also true for the cross-platform user interface. You can add multiple property packages. You can add more than one instance of a single property package. You can also do the same with the flash algorithm. Okay. You can make your selection of the desired property package and flash algorithm here in the property package section, which is on the beginning of the editor. Okay, so you can select, and the DWSIM will calculate the string.